Tonight we're going to look at 581, the Blazing Bulldogs code. We looked at their robot last week, and we went through their CAD and kind of saw how everything was put together. I don't think we actually saw one of their matches, so we can very kind of quickly just see the robot architecture and make sure everybody understands it. So you can see they have like the algae pinch arm there. They can go up and grab algae. They can come back, grab coral with their intake, and then swing it back on and place it pretty quickly. So we'll be able to find all those mechanisms in code and kind of see how they go through setting everything up, and then how they do some of their control logic and things as well. All right, so I went through and I already downloaded their repo and have it open in Visual Studio Code, but I haven't really looked at it other than that. So we can start seeing a little about how things are laid out. We have their main source and test folders. So we can see they actually are doing quite a bit of tests in here, which is cool. So that's something that we haven't done very much of, but definitely something that we probably should be doing more, especially just to like check some of our math. I'll kind of look through how some of that works here. Then they have a few other things. So they have the tuner swerve project. So I think this is what comes out of the CTRE swerve setup, so they can do the configuration that way. And so that's a very valid way to configure swerve modules and things for robots. It makes it a little bit easier. There's like a UI and stuff you can use to go through and get everything set up correctly. So that probably means they're using a lot of the CTRE swerve stuff, similar to how we do a lot of our swerve as well. We wrap a lot of it and put some things around it, but it's definitely not necessary. I don't know what some of the other things are. Yeah, I'd have to go look at what Renovate is, but it's probably not too important for what we're doing. Oh, and then they actually have a tuner swerve project and a comp tuner swerve project. So that's probably the two different robots. They can just have the different JSON files and potentially just switch between them, which would be pretty useful. Okay, so up in their main, we can look at kind of their main software. We can already see they have a lot of folders, which is nice. So it's organized, maybe easier to do some things to keep everything organized. We see robot. We don't see a robot container, but there is quite a bit of stuff going on. Like a lot of imports means they're pulling through a lot of all of these different folders and things. You can kind of see a lot of them are all laid out again here, which makes sense. They have to all be coming into robot somehow. They have a whole FMS subsystem, which I'm guessing is custom. I don't think that exists before. Yeah, so they made some things like that going back. They have a life cycle subsystem. Oh, so that's how they're adding in some of like robot periodic and things into. Okay, interesting. So even though, because they're doing that in timed robot. So there's a couple different templates and how the robots can work. That's still iterative. So some of that still exists in here, I believe. This is back into like the WPI lib file and things. This is probably deeper than we need to go, but potentially useful for some of that. I don't remember if that's all part of it or not. Yeah, so this still has Auton and disabled in it as well. And so these are the standard methods we use for the WPI lib versions. But then they're doing some of their own in this FMS subsystem. And so we'll have to figure out kind of somewhat why they're deciding to rewrite some of those things with the lifecycle subsystem and stuff as well. I assume there's a good reason, just don't know what it is yet. Saying they have an entire hardware. So this is where they're defining their actual motors and things are just all in their own hardware class. So instead of defining them and creating them in each mechanism and having the mechanism handle the creation of each actual hardware instance, like how you would talk to each of the motors and things, they're doing that all in a single class and then pulling the configs from their robot config class for each one, and just generating the object, but they're not like initializing it or anything either. So they just have the object generated here. It's final, so it can't be changed. You can't like deploy on top of it or anything. But that seems to work for them as well. And then they have some of their other subsystems deploy. I don't know if that's like intake deploy or if that's just, yeah, that's just one of the subsystems. Okay. Swerve, IMU, multiple limelights. So there are 4 limelights set up all here. They have a full vision subsystem that takes in those limelights as arguments and the IMU that they're using. And so that's the Swerve drivetrain pigeon goes into an IMU subsystem. For the IMU is inertial measurement unit. So that's what we often just call the gyro, telling us how far the robot's rotated. It has more stuff going on. There's a gyro accelerometer, technically a magnometer in there as well. Largely, it's there to make sure we know how far the robot's rotated from its initial position. And so they're going to have some of the code in there for that. Localization, they run that as a full subsystem. So they kind of follow a model that we follow a little bit too, where just everything is a subsystem. And that helps keep things kind of straight. It allows things to have their own periodic and things. If we go into localization here, you can see that it it's extending. Oh, so this is actually extending state machine, not necessarily subsystems. So they're going to do a lot more of their things on their, I assume is their state machine class. Yeah, so they have an abstract class that they create for state machines. And so that's how that's working. But they just call it all subsystems, even if it doesn't meet the actual like subsystem base. But it does have, okay, so it has a method for robot periodic that gets called somewhere. I'm sure we'll probably dig back into this a little bit later. Yeah, so every state machine has a robot periodic, has some other things for get state. Let's see. Yeah, that makes sense. So yeah, that's actually that's a pretty interesting way to do some state machine stuff. We'll probably have to look at that as we go deeper into this robot or into the software. Then we get their elevator, something called a trailblazer. Okay, so this is how they're doing some of their path following things, right? So given a point and the constraints for its parent segment, resolve the constraint options to use while following that point. So this is something a little bit different than Path Planner. They have a path tracker and a path follower in here. And so, yeah, so they have followers, trackers, things like that set up to do some of their Auton a little bit differently than how we did any of ours, right? It doesn't look like they're just using Path Planner directly or anything like that. They're going through and writing some of the underground things that Path Planner just kind of does for us, and the Path Planner run things that exist inside our library as well, or like we're from their library that we use to run the Path Planner commands. They're doing some of those on their own, it looks like, or all of it on their own. They have a rumble controller subsystem for driver feedback, claw, intake, arm, lights, probably LEDs. There's their climber subsystem, auto align, quarrel map, ground manager is the deploy and the intake. So those are a combined class for both the motor that actually moves the intake in and out, that deploys it, and the motor that intakes the quarrel itself. And then the robot manager takes in all of those things, and so they pass all of them to a different class for robot manager. Yeah, that's what it looks like. And then they have some more things like a field calibration utility that takes in multiple of those objects as well, for certain ones at least. And then a full robot commands class and autos class that again takes in instances of all of these. So yeah, they're building up a lot of the stuff in robot and then passing all those references or those objects into the other classes to create them all and make sure they have a way to use them. And so this lets, yeah, so that's one of the differences here is like all of their things here are fully private, where we largely just run it all public and just let the files access it directly. Could that cause problems? Probably, but also we're the only ones writing software for our robots, so you can get away with it. But this works as well. Doing it all private and then passing them all as arguments totally works. You just then have to, like, if you end up needing something else in Robot Manager, you just have to edit the constructor for Robot Manager to make sure it knows, hey, I need to add another argument to pass something else into it. And so you just add that in anytime it needed to access anything new that you added into here or anything like that. So yes, relatively standard stuff through their robot, printing the serial number, silencing the joystick connections only if it's in simulation. So if it's in on an actual robot, they'll leave the joystick connect warnings there. Starting signal logger, so we can log all of the. That's the signal logger for CTRE, I believe. Yeah. So that gets them their hoot file, which logs directly from the motors to on the RoboRio. So you can do some things that can be displayed in different places and used differently. So there's some logging that doesn't even have to happen on the RoboRio. You can get some logs directly from the CTRE devices. And then they have them setting up dog log. Let's see. Yeah, logging some basic things from like the build constant. So you can generate this from Gradle and it'll tell you like when it was built, which Git branch it was built off of and things. So all that can be logged. So when you look at the log file, you can see, oh, this was running old code because I know what like Git commit date or branch it was on or when it was built or anything like that when that code was run. So it helps for identifying when the logs were run or if there was some problem just because somebody had pushed older code or a different branch or something and it ended up running at competition and you didn't expect it to. So logging that sort of things are useful. And you can do that when it's built so that when you commit it over and send it to the robot, you know some of those things in a build constants get set up that way. Okay. Then they just end up doing some lifecycle things, making it ready. Oh, they have an elastic layout utility. And they have collision avoidance things here. Not entirely. So that's going to be a lot of how they make sure the arm's not crashing into the base and things, I believe. Or into the intake or anything like that. That's kind of what it looks like. Yeah, so they have like superstructure position, making sure the routes are getting there. It would definitely take longer to understand exactly how all of this worked as we follow through it. Yeah, you can see find the closest lowest multiple, so the unwrap angle. So yeah, so they can make sure they can move their arm to the position they need to in the quickest way for some of those things as they're unwrapping 360 because you wouldn't want it to like have the whole arm because their arm I believe can go continuous rotation, kind of like the wrist on our 2025 robot can. So you wouldn't want it to just, if you only told it to want to go like 3 degrees backwards or 5 degrees backwards, you wouldn't want it to go 355 degrees the other way. It would still end up at the same point, but it would be really inefficient and potentially crash into things. Let's see, a blank robot init. So they're not doing anything at the start of robot, which is interesting. But I guess some of that is all happening just on robot. So these two things are basically the same. Anything that runs in the robot constructor and robot init are largely the same things. Because this is also run once at code start, and so is this method. So I believe this is going away at some point, but I'm not sure if that was finalized or not. in like the WPI lib templates. Let's see. So yeah, robot periodic. They're doing mostly log things. They have a log for low battery. And then let's see. Yeah, some field calibration log stuff as well. Different layout utility things for when it's disabled or enabled. Yeah, tests, they're just canceling all of their scheduled commands. So you can get instance and cancel all, so it cancels every command that could possibly be running when they go into test mode. Yeah, teleop init, they make sure to cancel the auton command because you wouldn't want the auton to keep running if you start going into teleop. All right, and then towards the bottom we have their configure bindings, which are normally some of their robot ones. Yeah, so you can get some, so they're setting up a swerve default command here for how to drive. So this is all where they're like using their hardware.driver controller and mapping these things to their functions. And so those are the 3 stick axes. You need to drive swerve, right? Your X, Y, and then your right stick X for steering. And then they have other things going. So you have your triggers and bumpers going to confirm score, floor intake, algae intake, stow, and then they put some other things on, some bumper presses for on true and all on false, lineup, and then scoring a line off command. So if you're holding Y, you're going to go line up for your high, which is like L4 or barge, and then you would confirm it with the right trigger when you're ready to actually score. And then whenever you release, it just stops the auto align. And so they're doing that for X, B, and A as well. So low, L2, L3, and high. You would assume low is also processor, and then L2 and L3 are coral and algae, level 2 and 3. Let's see. So your POV, up, down, left, and right are your D-pad on the left side of the game controller. And so that's how they're doing their climb. So POV up is climb up, climb down. Left gets you a low store, and right gets you algae reef intake. Okay, so yeah, so then your L2, L3 may not be for algae. You may only do that on your POV right. And then we'd have to check, but it's very possible it just knows where the algae is supposed to be at those right heights. And then we have a few other buttons. So your start and back buttons are doing your unjam and your get 0. That's normally your like, oh, that's your resetting the gyro 0. Which does make sense. So that's how they can reset the gyro. If it gets off, they can get it aligned manually and then press that button to get it back to 0 correctly. Then they do have an operator controller set up for a few things. Rehome the elevator command, rehome the deploy command. They have a spin to win command, which is probably, let's see, so robot spin to win. Yes, they're just doing that. We can go deep dive anytime you see something like that. You want to know what's happening. Climbing, as long as we're not climbing or rehoming, and spin to win flag is set to true. Robot prepare spin to win. So we'd have to go through and figure out where all that is. But a lot of times the direct manual spin is, this could be their like arm doing it because it can fully rotate. This could be them just having a way to spin the robot a certain way to try to unlodge stuck game pieces or something. We don't entirely know what spin to win is. It could also just be some other form of emote style thing that they want to have a button for. Lollipop command is figuring out how to get. Oh, that's on robot commands. That's not. That's going to be an auto. We're back over here. Okay. So operator left trigger. Oh, is the next thing. So test next lollipop. So yeah. So that may be um, potentially going to grab one of the coral lollipops or anything, depending on where they are. So we'd have to go through and look and figure out what this command does. It's a reasonable enough point to go through. I think most of these are just going to. Oh yeah, we can see. So switching on state. Coral lollipop approach, grab, and push. So yeah, so this is somehow grabbing the coral lollipop off like the spike marks at the start of the match, the ones that are stood up vertical. So they have some way to go up and go and grab those with a specific command, it looks like. That also may just be like a test thing as well. Since it says test, that may not have ever actually been running. We have to find out. Like a lot of people, you'll still leave some things in there that aren't necessarily required or don't actually get used in matches. All right, let's go see how some of their subsystems work. Intakes are normally a pretty good one to look at. They're normally pretty simple. We know it's like some sort of roller. So intake subsystem, it also extends just state machine. It has a Talon FX motor, but you basically just pass in a motor and that they configure it and then save it as motor inside the subsystem. So they're doing that basically every time. So they're not having to like necessarily have the configs and things in this class. That's kind of handled somewhat outside of it, right? So you have the robot config file doing a lot of that. That work here. And then we know in hardware, they also have this motor because that's the one they're passing in. And then they can use it here as they store the same object in the local private variable for the motor here. All right. So collect inputs. Normally on the state machine, they are able to do this. Let's see if we can have that set up. So when you have like a collect inputs, those are all going to be like running first. And they have other things running after it. So yeah, so in their robot periodic, they basically see the first time the robot boots up, we need to set the state from null to the initial state to run state actions for an initial state as transitioning from the robot being off to the initial state. Okay, so basically, if it's not initialized, you need to like do transitions before you can actually collect inputs potentially. And so then you're able to collect inputs, which basically lets you do any of your like sensor data, get it all from all of the other mechanisms. Because that's one of the potential issues in our code is that we kind of run things in order. And sometimes we don't necessarily know the order of how things are going to run. Like the intake periodic method might run before the elevator one. And if the intake needs to check something of elevators to know if it's going to hit or if it's going to do something, it might be like a cycle out or a cycle behind if they get run out of order. For most things, that doesn't matter. The robot cycle, the code's running quite fast, 50 hertz. So it's happening, 50 times a second. Most of the time, it's okay if it's getting slightly old data. But there are times where having it as fresh as possible and doing all of your sensor reading and sensor math first for all of your mechanisms, and then basically at the end of your cycle, setting all of your motor outputs does make a lot of sense, right? You take in all the information you can, and then change all the states basically at the same time. And so that's what collect inputs is doing, and then set state from request, get next state is going to be the ones that actually set the states and then allow the motors to do what movement they want, is how I understand it to work. But I also haven't wrote code like this before, so I could be wrong. So a lot of this is set up for creating some commands for how the states work. Let's see. Oh. Yeah, so after transition, so this is where, like it says, this is where you run state actions. So this is where you override things for like which state is going to be what it's going to actually do. All right. Yeah, so we should be able to see some of that in here in intake. So here it's looking through and it has a sensor on the intake. And so it's checking some of those things. If it's in simulation, it's going to do more stuff. And then we can see after transition, depending on the state, it's going to basically have a state machine in here for each of its states and tell it what the intake should be doing. So this is a relatively simple way to do that. You're basically saying, okay, if we're idle and don't have a game piece, we want the intake motor to not do anything. We want it to be off. If we're idle and do have a game piece, we still want to, we're going to set the voltage to 0. While we're intaking, we're setting the voltage to 12. While we're scoring, we're setting the voltage to -4. While we're hard scoring, we're setting it to -6. When we're doing the handoff, we're setting it all the way to -12. So that means they're able to like push the coral out of their claw with more power when they're handing it up to the gripper to go to the higher levels. But when they're actually doing L1 scoring with their intake, -4 and -6, they want those to be going slower so that the coral doesn't like shoot out and go either too deep into the reef or bounce off the reef back into the robot or anything like that, or knock other coral out of it. And then their unjam is just -6. So they found that they don't need to do the full handoff eject here. They can just do a smaller one and still unjam depending on what they're doing. So this is a pretty simple way to set up the state machine for a single subsystem. These are all the different things this motor can do in the different states it can be in. And so this is all in just like a single method. And so then all of your other things in code are just, depending on the overall system state, is telling the intake to do one of these things. We can see if that gets, let's see, more complicated in some of the other ones. So if we go into like, oh, actually, before we do that, let's stay on intake real fast because we didn't actually look at intake state. So their intake state file is just the enum representing each of the states that the intake can be in. So that's relatively easy. This could be included in the intake subsystem file if they wanted to. You can have it out separately and have it know exactly where it is pretty easily, which is nice. And it doesn't take much because then they import it. Let's see. Yeah, because it just comes in as intake state. Oh, that's the different. Yeah. Oh, yeah. So because it's coming in as intake state here, they're able to know it already exists because it extends state machine intake state. So that's why it has to be in a separate file, is because they make it a enum with the state here. So because this is the way this is defined, they basically have to have a enum because this is actually kind of built into the way the state machine class works is you have to pass an enum into it or tell it what type of enum it's based on for your state is the way they do that. So that's relatively clean because you always know where your states are. So you can define a lot of those early on. We can define everything that the intake's going to be doing, the elevator's going to be doing, the swerve's going to be doing, any of our subsystems. or the subsystem for the robot, you can define their states specifically, and then you just have to get the code right to actually do the things you need it to do in those states. And I imagine it gets a little bit more complicated with some things like set state, because if depending on what state you're in things, you can have more logic in here deciding what your next state is, or how to clean up your old state or anything like that. So we may be able to see that in some of the other ones. Stuff up here real fast. Let's look at one more mechanism. Yeah, we still got time. All right. So let's try elevator. So if we look at elevator state, we get a lot more going on. All right, so intake was probably one of the simplest ones, if not the simplest one in this robot. Now your elevator states have a lot more going on. We get the actual name in the enum, but we also get a value. So they're able to just define those values here already. And they're able to have some methods that do things on them as well. So so these are constructors, right? So for climbing, height 0, that's basically equivalent to like this state, and they're passing in height, right? So this double height is what all of these values are. That's why you have that height colon there expanded for us. And so they're also able to tune it. So they're able to set that as a tunable parameter in how Doglog's working, which is very cool. So you could go in for each of your elevator states and the name. They should be able to just tune those in Elastic or any of the other smart dashboard editors. And we can tune those values and change them while the code's deployed. So we can get those set, and then we can come back in here and type them into here to get them set permanently. So that's a very simple way to do that, and a very nice way for something like an elevator where you just have a lot of these configurations, and you're not having to do it in a config. It kind of all gets built in for you, and the name of it automatically pulls the right height for each thing, because it's all just set there. So that allows elevator state to also be somewhat of your config file as well. Yeah, and then their get height method pulls the tunable height directly. And then, yeah, it doesn't seem like there's an easy way to get default height. Yeah, that shouldn't be a problem. Okay. So then in elevator itself, or elevator subsystem, yeah, so it's a state machine passing in the elevator state enum, some other tolerances and near tolerance. So basically say if we're within 0.5, that means we're close enough. Near tolerance may be something to like slow it down, or say if we're near, we can start doing some other tasks, those sort of things. Clamp height is there to make sure that you don't tell it to go to an invalid height, so you can't tell it to be like negative on the elevator. If the elevator starts at 0 is full down, you don't want to try to command it to go to -10. And then same with like whatever the max height of the elevator is, you don't want it just to go, you don't want to command it past the max height of whatever the elevator can do. And so clamp height is just a quick method that forces that. That's what mathutil.clamp does. And so that'll come back and return the double correctly, and so I'll use that somewhere in here. Elevator has 2 motors, and so they set them up both there. Some form of linear current filter. position request, stowed. Okay, so their position request is defaulting to their stowed height. And their height is getting passed straight to motion magic voltage. Yeah, so their motion magic voltage is getting past a position, and so they're just defaulting it to their stowed position. And so that's just getting sent to the Kraken motor controller, and it's doing all of the control logic on board. That's the same way we would do elevator or anything like that. All right, let's see. Motor current stuff, a lot of diagnostic things which are good. Setting up the motors, setting up some tunable PID things as well. So able to potentially tune the PID values for the motors directly in Elastic. Normally what tunable or something like that does is you can do it while the robot's running. The set state for elevator is a little bit more complicated than it is for intake. You don't just immediately do it. You do see if you're pre-match homing, mid-match homing, or your default is just set state from request to new state. So based on what the state is, it's going to do a couple different things. Yeah, okay. Let's see. Yeah, so collect inputs again is just taking all of the sensor data, so they're getting the left motor, get position, get stator current, calculating the current filter, and then if we're disabled, doing some other things as well about last seen height, getting set only if they're disabled. And then the states here end up actually being pretty easy because you basically just switch on new state. And if we're mid-match homing, we do a certain thing, right? We set the voltage to -0. If we're doing collision avoidance, they have some things with the collision avoidance goal. So there's their collision avoidance method here. Does that get? Yeah, so set collision avoidance goal is there. This has to get used somewhere probably in, oh, so that's getting used in Robot Manager. So we'll go look through Robot Manager after this probably. And then so if they're not in collision avoidance mode, every other state is just setting it to the new state height. So that ends up being pretty easy because basically every state of an elevator is either we're homing or we are just telling it to go to a height that we want it to go to, or calculating that height in a slightly different way with collision avoidance. All right, and so they do a little bit more periodic stuff here for some logging. I'm not going to spend too much time on that. And then their get next state, because that's after transition, but figuring out next state from current state has a little bit of things too. So basically for their mid-match homing or pre-match homing, they do some things. Otherwise, it's just current state all the time is their next state. For mid-match homing, once they are, once the average currents are greater than some homing threshold, they become stowed. And same with pre-match homing. They just do them a little bit differently. And then, yeah, so you can check if you're at goal, near goal, other things there, and then we get into their periodic things as well. Okay, so let's go look at Robot Manager, because I think that's where a lot of their actual stuff happens. Yeah, so we can already see this is a pretty long file. So we're getting into that 1700 lines of code bit. And this is probably their main state machine for most of the robot. Right, so it's bringing in every subsystem, or the vast majority of them that they have. Yeah, and so you can see all the different states. I think there's probably, yeah, I would say robot state exists up here, so you can start seeing everything that the robot can be doing, not just what each subsystem can be doing. Starting position, curl intake. Yeah, so these are all specific intake states. L1 scoring states, all of the different coral scoring states, all the different algae scoring states, climbing states, miscellaneous states. And then they have some more here where they're getting lineup to place, so they have their left lineup and left lineup place, and they're kind of mapping these all together. Let's see, what else is worth commenting on? Yeah, those are just the methods to pull the states out. Yeah, that looks about right. Okay. Oh, I left the other one down here. Robot Manager. Okay. So, yeah, so all of those states get defined in the other states file. And we can kind of see all the different things that happen based on some specific cases. So yeah, that's all current state, and then all of the various cases here. How are we looking at? How does this get cleaned up? Okay, so yeah, so some of those are relatively easy for our get next state, where they're just going to set to current state, right? So all of these are ones that they're just going to keep setting to current state. Other ones have to do different things, and then they yield the current state. Some of the others, depending on whether the claw has a game piece or not, right? So like rehome elevator, if we're at stowed, we set the state to claw empty. If we aren't at stowed, we set the current state, and we keep going back and forth. Or keep looping through again. Same with like the L2 right approach. If the elevator is near goal for lineup and the arm is near goal for lineup, we're able to do current state dot get right approach to lineup state. Otherwise, it's just current state gets sent back. Yeah, so these are all the different ways that as it's figuring out what the next states are, you can go through all of those. And then after transition is what actually happens during the state. So these are where you actually tell everything to do something. So for each of the robot states, you're able to go through and say what each thing should be doing, and basically setting a state for each of your mechanisms to be doing that thing. It's a good one to look at. So yeah, we can look at all of those are scoring ones. Intake. Yeah, so algae net left release. Claw is set to score algae net. Move superstructure to elevator algae net. Arm to algae net left. Swerve normal drive request, vision to tags, lights to scoring algae, climber to stopped. And so then all of the other things, and you're like not really worried about what intake's doing here, so you don't have to assign it. Because it should already be back to its default or anything like that. Yeah, and so you just go through and do that for each of the ones that you have every state that you need the robot to be done for. And they have them all defined, scrolling all the way through this file. All right, so yeah, on their periodic, they're going through, they're doing some basic logging things. And they have another switch here on the current state. And it sets some things based on which state it is. They're able to change vision a little bit. Oh, because they switch from vision state handoff to vision state tags, because they're using the cameras to know where the coral is in their handoff. And so they're able to do that if they need to. Algae intake is scoring alignment to reef angle if they're in any of those algae intake modes. They score align to the reef angle instead of in the normal drive request. Same here. All right. Yeah, so then they're just defining, oh, and their collect inputs, they're figuring out what scoring level and things they're on, so they can log quite a bit of this, I imagine, use it in other places if needed. Some code to make sure they can stow correctly. Yeah, there's definitely a lot going on here to make sure everything is working right. I don't want to get too far in this. I definitely need to read a lot more to know how all of this is working. You can get a rough idea as we kind of scroll through. Okay. Far down, right. All right, we're mostly through that. Yeah, there's definitely more to that we could dive into. I just don't want to spend all of our time doing this, so I was trying to figure out if there's anything super different in there. I didn't see it, but I'm almost certainly missing stuff. I'm definitely not reading or comprehending all of this quickly. I was just trying to see if anything popped out, because there's definitely more stuff we can look through to see how some of their things work. What did I want to go into? Some of their auto things would probably take a while, but we can look at the very beginning of some of it. Let's see. So they can see some of their like actual what their auto paths are. So these are their different auto paths that they have for red and blue. And they're creating these command sequences for each of those. So yeah, home deploy, preload coral, timing.time. I'm not sure where some of that exists. Okay, so that's in their base auto. So that takes in Robot Manager and Trailblazer. And then they start getting their starting pose and creating auto commands. And And so a lot of that is going to, yeah, so all of these extend base auto. So all of this is like their default setup. And then they override a lot of it. So that create auto command, I guess create full auto is different than create auto. So that may be a different place in here. But yeah, that's calling create auto here. And so this is some of their getting the total time it takes for all of this. Checking is auto enabled, those types of things, just to make sure their auto can actually run. And then what actually runs is happening in here. So some of this is like timing different parts of the task so they can know how long some of their auto segments and auto tasks take. Trailblazer is there to be able to follow those line segments. And so now, yes, yeah, so they're creating the auto points. So they are also doing some point-to-point auto creation and being able to follow through those to get to each thing. So yeah, so you can have the different ones of each of the lollipops, which are the poses they go to, telling it to then score L4, intake lollipop command, drive to the second lollipop, and then do that same thing, intake again, drive to the third lollipop, and then score it as well. So they have some things that are just like blocks. So like the score L2 is a specific thing. So they're going to tell it which pipe to score on and which robot scoring side. And then it's going to figure out, okay, we're in this auto segment. Our auto point is figuring out what their scoring pose is for the pipe that they passed in here. So we have a method that's able to give them that position of where the robot should go to score on that specific reef pole. And they set auto reef override to do that. So they're going in to score basically at the reef and make sure they're using the right April tags and things and right alignment that they want to be using for that. And they're waiting for states to make sure the claw is in coral mode. They're on the left-right approach, and they have starting position coral, and then for states, yeah, and then L2 lineup with deadline, follow segment, after score position. Oh, and they have a wait for release command. So that's after whichever one they scored on, did they actually release the coral to actually do the scoring. So that lineup command is probably doing all of the actual auto score as well. Let's see. Yeah, so that's basically telling everything. If is autonomous, set state request, coral L2 left lineup. And so that's going to go in and auto score everything. Yeah, that makes some sense. Okay. And that only happens if they have a game piece or ground manager says they have coral, right? So either the claw has the coral or the ground intake has the coral. Are they going to run that? Because if they didn't run the coral, they're not going to score L2. They're going to come back and basically like try to grab the next coral. Yes, that's how most of their things work. A lot of this is just those points being set directly. It looks like they're all just being hard-coded into these paths. I'm not sure if they have a way to edit those or find those points easier. We'd have to figure out where that would live. I think that's most everything we have time for tonight. there's definitely a whole lot more to look through in this. I will probably spend some more time at some point going through it. Don't know if we'll get that on one of these videos or not. There's still a lot to learn because you can see a ton of just the way they set this up is very different from the way we do it on Spectrum or the way kind of the default WPI lib is, but they're able to do a lot with this. It's definitely a very powerful setup.